So, what are organic compounds? Well, they're generally compounds that are made up of carbon and hydrogen atoms. They'll contain other nonmetals too, such as oxygen, sulfur, nitrogen, phosphorus, and other halogens like chlorine, fluorine, and those kinds of atoms. But most of them are composed of carbon and hydrogen atoms. They're found in all kinds of stuff around us, like gasoline, medicines, shampoos, plastics, and perfumes. But the thing to know about carbon based compounds or organic compounds is that they generally have covalent bonds. They have a very low melting point and boiling point. They're flammable and undergo combustion, and they are commonly not soluble in water. Uh, so formulas of organic compounds are written with the carbon first, and then followed by the hydrogens, and then any other elements, and we'll see that later on in our lecture. So over here is just a comparison between organic compound and a inorganic compound, right? So the organic compound is the CH3, CH2, CH3. That's actually the the formula or the structure for propane, which propane saved my life during the winter storm because we had a propane grill out back. And if I had not had a propane grill, we would not have had any hot water. We would not have been able to cook any food. It would have been an absolute disaster. So thank God for our propane grill. But propane is, as you can see, made up of 3 carbons, right, and 8 hydrogens, or arranged in the way that you see in that structure right there. Now, if you compare that to this table salt right here, which you remember from previous lectures, contains sodium ion and chloride anion, right? They're not sharing any covalent bonds. It's an ionic bond, of course, right? And they are in a crystalline structure, right? So that's things to know the difference between. The next slide here is actually a very good summary of organic versus inorganic compounds, right? So let's just briefly go through this, but it's a good thing to look through this and familiarize yourself because there will be questions on the assignments, quizzes, and exam about these kinds of things, right? So organic compounds, right, always have hydrogen, carbon and hydrogen in them, but sometimes have oxygen, sulfur, nitrogen, phosphorus, or chlorine, or some other halogens in them, right? Of course, an example of that, carbon and hydrogen. Here is propane, right? That we saw on the previous slide. These are mostly molecules, right? Well, actually, I take that back. All organic compounds are molecules in their natural state, that the way you see them. But in inorganic compounds, they are mostly in ionic form, like they're in ions, in ion form, right? Like the sodium ion or the sodium cation or the chloride anion, right? They're definitely mostly covalent. There are some organic compounds that are called organometallics, and there'll be organic compounds that have some metals in them, but most of all of them are covalent compounds with covalent bonds. And then in inorganic, most of them are, or many of them are ionic bonds, right? But they do have some covalent bonds. And then the polarity bonds, of course, in organic compounds, they're nonpolar unless there is an electronegative atom present. So remember, an electronegative atom might be something like oxygen, right? So you could have something like that, which is ethanol, which makes it slightly polar, right? Whereas if you just had that without the OH at the end, since there's no oxygen, that's just ethane instead of ethanol. That's nonpolar, right? So that's the difference. So unless they have something like an oxygen in there, or maybe a halogen or something like that in there, they're nonpolar. Inorganic compounds, though, they're mostly ionic, right? Of course, there are a few that are nonpolar covalent, right? And the next few are the important things, the important properties that you need to make sure you're aware of, right? Organic compounds have very low boiling points and have very low melting points, right? You know this, for example, um, I don't know, for example, like isopropyl alcohol. Uh, I use it a lot in 3D printing, but most people use it to sanitize their wounds before like a shot or something. Like if they're getting a shot, they use that. But you notice that as soon as you wipe on the isopropyl alcohol, it evaporates, and that's because your arm is warm enough that it evaporates the alcohol immediately, the isopropyl alcohol immediately, because that's an organic compound. Um, on the other hand, though, if you had something like water, right, which is also which is not an organic compound because it doesn't have any carbon in it, right? But water takes forever to dry, as evident from all the water from the leaking from all the winter weather, right? Another thing that's important is the boiling point of organic compounds. I'm going to use ethanol again as an example. The way they make ethanol is by distillation, right? When I was teaching biochemistry at Auburn University, or maybe it was at Sam Houston State University. I taught biochem at both. I can't remember which one. But at one of them, we were doing an experiment where we were distilling alcohol from yeast. So, how do you make alcohol, like the type of alcohol that you drink? Well, you have to actually ferment it. So you'd add yeast to some water and then add some sugar to it, right? And they go through a process called alcohol fermentation. And they produce ethanol, which you can drink, and uh, carbon dioxide, and that's called ethanol for alcohol fermentation. And so, but the problem is that you have the yeast in there that's still in the liquid in that mixture, and you still have the water in there, and you really want to get the water and separate. You really want to separate that out from the ethanol because that's all you really want, the ethanol. So what do? You do distillation, and distillation works on the principle that alcohol or ethanol, what you drink, has a boiling point of like 78 degrees. I think it's 78 degrees Celsius. It might be 74 degrees Celsius. Someone check that for me. It's either 78 or 74 degrees Celsius. Whatever it is, it's still way lower than what water is, which is 100 degrees Celsius, right? So when you distill it, you can actually distill it so that the alcohol evaporates and the water stays behind, right? And then you can condense the alcohol in a separate flask. And so that's called distillation. And that's how you get your alcohol that you can drink, right? So the example they have here is, again, we have propane, right? And its melting point, holy mother, is 188 degrees minus negative 188 degrees Celsius, and its boiling point is minus 42 degrees Celsius. So it's pretty low boiling point and low melting point. I'm trying to remember. I think it's Titan, the moon around Saturn. It has lakes of ethane, I think, or methane. One of those hydrocarbons. I can't remember which one. But it's so cold there that there are lakes of these things, right? There are lakes of ethane, which is crazy, right? Flammability, of course, is really high. We already talked about how I use propane to cook my food and boil my water during the winter storm, right? Very high. And ethane is definitely not soluble in water, right? But on the other hand, if you want to use salt again as the example here, it's ionic. We already said that before, but it has a very high, very very high melting point. It doesn't melt till 801 degrees Celsius. It doesn't boil until 1413 degrees Celsius, and it just doesn't burn, right? And it is absolutely soluble in water. That's just a really easy, two easy examples to compare organic and inorganic compounds. And this is the difference between propane, which is the organic molecule, and sodium chloride or table salt. As the inorganic compound. So some more details about hydrocarbons. Of course, they contain carbon and hydrogen, but the thing to know is that every carbon in a hydrocarbon has 4 bonds. So in this very simple example of methane, we have a carbon in the center with 4 hydrogens around it, covalently bonded to the carbon with 4 single bonds, right? Then what is a saturated hydrocarbon? A saturated hydrocarbon is one in which all the bonds are single to the hydrogens where available, right? Doesn't count this one in the middle that connects the 2 hydrogens together, right? So this is a molecule called ethane, and it's a saturated hydrocarbon, right? Well, what is an unsaturated hydrocarbon then? Well, an unsaturated hydrocarbon is very much like a saturated hydrocarbon, except now there is a double bond between the 2 carbons, and so the only available space are 2 bonds each for each carbon, right? And since it's no longer only single bonds here, this is an unsaturated. Unsaturated hydrocarbon, right? We'll learn more about this when we start talking about alkenes, but this is named ethene. This is named ethene. So now a little bit about the geometries of carbon compounds. We're using methane as our example again, right? It's got carbon in the center and 4 covalent bonds to 4 different hydrogens around it, right? That makes methane a tetrahedral geometry with bond angles of 109 degrees. So down here, you actually see 4 different representations of methane that we use in organic chemistry. The first one is called a space filling model. That's filling, not filing, right? The next one after that is called the ball and stick model. The third one is called a wedge dash model. D here is referred to as an extended there we go, structural formula. You'll see these a lot in organic chemistry. We work with those a lot. And then E here, or the 5th one, is known as a condensed structural formula. So now let's take a look at ethane, which has 2 carbons in it and 6 hydrogens. Each of those carbons are tetrahedral, and they form 3 covalent bonds to the hydrogen and 1 covalent bond to the other carbon, right? And you can see that represented very well here with the wedge and dash model, how this is a 109 degrees as well, tetrahedral. And if you don't remember, whenever the wedge is dashed, like that one, it means it's going back into the wall or in the board. And then when it's solid, like this one, it's coming out of you, it's coming out of the board towards you, out at you, right? The first type of hydrocarbons that we're going to be talking about, or carbon compounds that we'll be talking about, are the alkanes, right? The alkanes are all hydrogen and carbon, as you see here. This is a ball and stick of hexane, right? And based on the IUPAC, which is the International Union of Pure and Applied Chemistry, if a molecule only contains carbons and hydrogens and only single bonds, it gets the name ane at the end, right? The suffix ane at the end. And so as we look at this chart, methane is one carbon, right, and four hydrogens. Only single bonds, right? Ethane is two carbons. Propane is three carbons. Butane is four carbons. Again, they're all single bonds and only hydrogens, right? Pentane is five carbons. It starts to get a little easier with the naming now because now it's just the Greek prefixes that we already know. Like hexane for six carbons, 14 hydrogens, all singly bonded together, as you can see. Heptane, which is 7 carbons. Octane, which is 8 carbons. Nonane, 9. Decane, which is 10. And it goes on from there too. Like dodecane, things like that. So when drawing structural formulas for butane, which is CH4H10, we have here the expanded structural formula. It looks very much like the one from methane and ethane, except instead of having 1 or 2 carbons, we have 4 carbons. And each one of those carbons are covalently bonded to 10 different hydrogens. And that's what we call an expanded structural formula. We call it that, I forgot to say, because we actually draw the bond here between the carbon and the hydrogen, right? In a condensed structural formula, though, we don't draw the bond between the carbon and the hydrogen. We just write how many hydrogens are there. So at the end carbon, obviously, you can see from the expanded formula there are 3 hydrogens. So in the condensed formula, we just have to write CH3 for 3 hydrogens at the end of that carbon. For a center carbon, right? Like this one here, how many hydrogens do you see? There's 1 and 2. So here in the condensed formula, we just write it as CH2. We can do that because we already know that these bonds right here are connected to carbons, not hydrogens, right? And remember that carbon can only have 4 bonds. The rest of these are just all butane condensed structural formulas, just in different orientations. But the one that's probably the most commonly used in organic chemistry, because these hydrocarbon chains can get very long, is known as the line-angle formula, right? And in the line-angle formula, you don't have to draw any of the hydrogens or any of the carbons. So let me clear this and draw it over here so that you can see it better. If I draw a line-angle structure or formula for butane, it's understood in organic chemistry when you draw this kind of formula that at the end, where there's no chemical or atomic symbol, that is a carbon. And the same is true of these peaks and valleys as well. In organic chemistry, if there's nothing there, it's considered, or no symbol present or written drawn there, it's known as a carbon, right? Those are all carbons. So notice in my line angle formula, I have 1 carbon there, 2 carbons, 3 carbons, 4 carbons. The same way I have 4 carbons in the expanded and the condensed structural formulas, right? So what about the hydrogens? Well, if there's only 1 bond here connected from 1 carbon to another, that means then that the end carbon here has to have 3 hydrogens bonded to it. That's assumed in organic chemistry when you have a single bond to a carbon and no other bonds connected to it. It's got 3 hydrogens on it. And then for the second carbon and the third carbon in butane, both are treated the same. We see that there are 2 bonds connected to the carbon. One to the end carbon, carbon number 1, and the other connected to carbon number 3, which leaves 2 empty spaces. And in organic chemistry, those 2 empty spaces are always hydrogens, unless otherwise noted. And that's why it makes it faster to just draw line angle formulas for many of the hydrocarbons are, because these line angle formulas can get really long and get super tedious having to write carbon and hydrogen over and over and over and over again. I think palmitic acid has like 16 carbons in it. That's a lot. I'll have to check that. I think it's 16, but I could be wrong. You know what? I have my phone right here. Let's check. Yep, I was right. Palmitic acid has 16 carbons. Imagine having to draw on 16 of those and all the hydrogens that go with it. That would be rough. That would be really rough. So alkanes can also be in cyclic form. Those are known as cycloalkanes. And they always have 2 fewer hydrogen atoms than their straight chained counterparts. So the straight chain counterpart in this case is going to be propane, right? Which we saw on the previous slides. It's a CH3 connected to a CH2 connected to another CH3. Now this is cyclopropane. Notice that it has 2 less hydrogens than propane does. Why is that? Well, that's because of this third bond right here. This third single bond here that connects the 2 end carbons to each other, making this a triangular shape. It's occupied one of the spots, one of the bonds that carbon has, that those end carbons have, right? So there's not a space for a third hydrogen on either of those carbons anymore, and that's why it's missing 2 hydrogens, right? All these circular looking or non-straight chain looking alkanes have the prefix cyclo in front of them, right? And they're all going to be missing 2 hydrogen atoms as compared to their straight chain counterparts, right? So we were just looking at butane. There's a ball and stick of butane right there. And here's the condensed structural formula for cyclobutane, right? And here's the line angle formula for cyclobutane. These bond angles in both cyclobutane and cyclopropane super strained, right? Because remember, carbon likes to be in a tetrahedral form at 109 degrees, right? And that's basically 90 degrees right there, right? Basically 90. And that's a triangle right there. So that's like 30 degrees. That's rough. No, not 30 degrees. What if 120 is divided by 3? 40 degrees. So that's some strained bond angles there. Those are very unstable molecules because their bond angles are so strained when carbon likes to be in tetrahedral form. Cyclopentane right there, ball and stick, looks a little bit less strained, right? Here's a condensed structural formula and its line angle. And then last but not least is cyclohexane, right? This is its condensed structural formula. This is its line angle for the cyclohexane. But if hexane were not cycle, it was just hexane by itself, it would just look like this. Right? That's its straight chain counterpart. Right? For cyclopentane, its straight chain counterpart looks like this. And then these are easy because we saw them previously, right? There's there's butane for cyclobutane, and then propane for cyclopropane. Oh, I didn't have to draw that. That was already up here. Whatever. Anyway, next. So, interestingly, hydrocarbons can form isomers, structural isomers. What an isomer is, it's a molecule with the same formula, right? But is connected differently, right? Its atoms are connected in a different way, right? So here we have butane, and butane here is connected in straight chain manner, right? But here we have an isomer of butane where only 3 of the carbons are in a chain, and then the 4th carbon is connected to the center carbon, right? So that would be an isomer of butane. Notice again, right? What is an isomer? Isomers are molecules of the same formula, right? Here CH4H10, right? Both of them have the same formula, but they are connected to each other. The carbons and the hydrogens are connected to each other in different ways, right? So the formal terms are straight chain, which we already learned in the last slide, and then the new one is a branch chain, and that's the branch chain. Alkanes can also have substituents too. Alkanes can actually serve as substituents as well. And so if it's a substituent, right, then it has the suffix or the ending ethyl or ill in it, right? So instead of being like methane, it's methyl, or ethane, it's ethyl, right? So a good example of that would be this here, which is ethyl, right? If we were to draw that CH3, CH2, and then put an OH there, let's draw a line angle that looks like that too, right? This would be referred to as ethyl alcohol, right? Because this part here is called the alcohol, right? Yeah, in organic chemistry, OHs are considered alcohols, but in general chemistry, they're hydroxides. And the difference is that an alcohol is connected covalently to the carbon, right? Whereas a hydroxide is an ion and is connected by an ionic bond to whatever, like a sodium, right? Another example here is isopropyl, right? And I forgot to say that whenever there's nothing there at all, when you're doing a condensed formula, that means that something else, like another substituent, can be connected there. Substituent, right? So we look at isopropyl right here. We would draw it out in its condensed structural formula here. And if I add an OH at the top, or an alcohol, it becomes isopropyl alcohol. That's how you spell propyl. The Y comes first. There we go. Propyl alcohol. Right? And we just saw this molecule in the previous slide as its own molecule, which was just isobutane. But when it's a substituent, it's isobutyl. And then halogens can also be substituents too, right? And they're referred to as fluoro, chloro, bromo, and iodo when they're substituents. So let's talk about naming some cycloalkanes with their substituents, right? So when one substituent is attached to a carbon atom in a cycloalkane, the name of the substituent is placed in front of the alkane's name. No number is needed for a single alkyl group or halogen item, right? The IUPAC name gives all the information needed to draw the condensed structural formula for an alkane. So here, let's use this as an example. We have a cyclohexane because it's a hexane, 6 carbons, and it's in cyclic form, so that's why it's cyclohexane, right? And it has a substituent connected to it, which is the ethyl group, right? And according to these rules, the substituent is placed first in front of the alkane name. And that's why you come up with ethyl, right? Remember from the previous slide, ethyl, cyclohexane, right? So let's try to draw the structure here for 1-chloro, 1,2-dimethylheptane, right? Well, we already know that the green part here, heptane, is a 7-carbon chain, right? And that's the base of it all. So let's go ahead and draw that. 1, 2, 3, 4, 5, 6, 7, right? And if we number these carbons, 1, 2, 3, 4, 5, 6, 7, right? The name tells us where everything is. For example, 1-chloro means that there is a chlorine on the first carbon. Right? As a substituent. And then 1,2-dimethyl means there are 2 methyl groups, right? 2 methyl substituents at the 1 and 2 carbons. It's a very busy carbon there. By the way, the first carbon is also known as the alpha carbon. So you might hear me say carbon 1, I might use it synonymously with alpha carbon. It means the same thing. So there's a CH3 there, right? And this is a line angle, so normally you wouldn't even see that CH3 there, right? It would just be a line, and then you would assume that the CH3 is there. So I'll go ahead and just erase that because now you know that that's supposed to be a CH3. And then on the second hydrogen carbon, there's also another methyl group. Because remember, it's dimethyl. Di means 2, right? So in organic chemistry, it's super easy to draw out a structure using the name because the name tells you where everything is. The properties of alkanes actually help us determine what we use them for. For example, solid alkanes, they can make up the waxy coatings on fruits and vegetables. And that helps them retain moisture, inhibit mold, and enhance the appearance of the fruit or vegetable, the produce, right? So specifically, for example, alkanes with 1 to 4 carbons are gas form at room temperature and are widely used as heating fuels, right? Like methane is used in our natural gas for our stoves, water heaters, and our central heating units in our houses. Ethane, propane, and butane, as I already said before many times. Propane grills saved my life during the winter storm, and then butane lighters, right? And then, just a quick reminder, butane is line angle drawing there with 4 carbons. Alkanes with 5 to 8 hydrocarbons are highly volatile, but they're liquids, right? They're liquids at room temperature. That makes them useful as just regular fuels, right? This is pentane, hexane, heptane, and octane. Interestingly enough, right, octane here has 8 hydrocarbons, but what is gasoline made of? Well, the gasoline that we put in our cars is actually known as isooctane, right? So it's an isomer of octane that's branched, right? Alkanes with 9 to 17 carbons are also liquid with higher boiling points. And they're found in motor oils, mineral oil, kerosene, diesel fuel, and jet fuels, right? So decane there, of course, that's 10 carbons, right? Alkanes with 18 or more carbons are known as paraffins. They're waxy solids at room temperature, right? And then things like petroleum jelly or Vaseline, which are semi-solid mixtures of hydrocarbons, they all have more than 25 hydrocarbons. So that's why we, take the shortcut of drawing line angle formulas for many hydrocarbons, because I wouldn't want to draw out all the carbons and the hydrogens for a Vaseline molecule, and you wouldn't either. And just as a quick review, right? Alkanes are nonpolar, which makes them non-soluble in water or insoluble in water. When you put an alkane into water, it floats, so it's less dense than water. And we know that they're flammable in air, like butane or propane. Alkanes are found in crude oil, and when there's a spill of oil in the ocean, right, those alkanes don't mix with the water, and they're floating at the top of the water, right, forming a very thin layer on the surface. But we need them, though, because those strong carbon-carbon bonds right there react with oxygen gas to make carbon dioxide and water, releasing tons of energy, right, that in a reaction that we already know as the combustion reaction, right? So here we have methane gas combining with oxygen, some heat right there, and you're getting carbon dioxide and water and tons of energy, right? And as I already said before, methane is the natural gas that's used to cook our food on gas cooktops in our homes and heat our homes. Thanks for that. Along with alkanes, we have alkenes and alkynes. Alkenes are simply hydrocarbons with double bonds between two carbon atoms instead of single bonds. That makes it so that their arrangement is trigonoplanar with bond angles of 120 degrees. A very common alkene is ethene or ethylene, which is C2H4. It's a plant hormone that's actually released by plants that promotes ripening of fruits, right? But the problem with it is that it accelerates the breakdown of cellulose in plants, right? Which is why when you keep your vegetables in bags like that are sealed, they tend to go rotten faster, right? That's all because of ethylene. Alkynes, on the other hand, just like alkenes and alkanes, except for instead of single or double bonds between two carbons, it has a triple bond between two carbons, right? That triple bond gives it a linear shape with a bond angle of 180 degrees, right? And the other thing to notice about this too, on both the alkenes and alkynes, is that on the alkene, if you have a double bond between two carbons, that means that those end carbons are only going to have two hydrogens each. And then for the alkyne, triple bond on the two carbons means only one hydrogen on each, right? Keep that in mind. So how do we name alkenes and alkynes as compared to alkanes? Well, in alkanes, we always name it with an ane, like ethane. Well, with alkenes, we just change the ane to an ene. So here we have an example of ethane. If it's the alkene version, it's called ethene, right? Or the more common name or traditional name is ethylene. For alkynes, same thing. Instead of alkane or ane for alkane, ene for alkene, or we would go with kyne for alkyne, or ine rather. So here is ethyne, right? Or the more commonly known ethylene, right? Another example, we have propane here, ends in ane. Propene for the alkene version, propyne for the alkyne version. Pretty simple. So now, how do we name cycloalkenes, right? Generally, we'll name the carbons of the double bonds 1 and 2. So here, for this cyclopentene that we have, right, 1 goes at the beginning of the double bond, then 2, and then the substituent group, which is the methyl group, is on the 3rd carbon. So we name it 3-methylcyclopentene, right? So double bonds always begin the counting of the carbons in the naming. And the important thing here is that we already know that it's a double bond because it's a pentene. And since the 3, or the 3rd carbon, is where the methyl group is, we don't have to actually put the 1 and 2 for the double bonds because it's already implied in the name. Now that we've started talking about alkenes, we can talk about cis and trans isomers. So we don't have cis and trans isomers because in alkanes, because when you have a single bond, the carbon on either side of the single bond can rotate freely, right, around about that bond. But in alkenes, the carbon is actually locked, right? It's rigid; it cannot rotate. And so now you can have substituents on either side of the carbons that can either be cis to each other or trans to each other. And as you can see by the drawing of the hands here, cis hands means that the thumbs are on the same side. Whereas trans hands means that the thumbs are on opposite sides, right? Imagining that this is the double bond right here and this is the carbon. So let's take a look at 1,2-dichloroethene as the example. This particular condensed formula can be expanded into these two formulas, cis 1,2-dichloroethene and trans 1,2-dichloroethene, right? And just as the two hands imply, the two sets of hands imply, if the chlorines are on the same side, then it's a cis 1,2-dichloroethene. If the chlorines are on opposite sides, it's a trans dichloroethene. But that only happens with alkenes. So let's look at a couple more cis-trans isomers. We have here 1,2-cis-bromoethene. Right? Sorry, I said that backwards. Cis 1,2-bromoethene, dibromoethene, right? Cis because they're on the same side, 1,2 because they're on the first and second carbon, di because there's 2 bromos, right? 2 bromines, which are bromos because they're substituents, right? And then ethene because there are 2 carbons connected with a double bond. Then here we have trans 1,2-dibromoethene, right? Trans because the bromines or bromos are on opposite ends, right? 1,2 because they're on the first and second carbons. Di because there's 2 bromos, and then ethene because of the two carbons right here that are connected by a double bond. Right? We also have another example here, cis-2-butene. But in this case, the substituents right here are not really substituents. They're just the rest of the molecule, right, of butene. And both of the N-methyl groups of the butane are on the same side. So that's why it's 2-cis-butene. Here it's trans-2-butene because the two methyl groups are on opposite sides, right? Opposite sides. So now that we've gone over naming alkenes, alkynes, and alkanes, we've got to talk about some addition reactions. When you have an alkene or an alkyne, right, which are double bond and triple bonds respectively, right, they can react with hydrogen gas and water to form different compounds. They're easily broken, providing electrons to form new bonds. So for example, double bonded alkene here, right, can be treated with hydrogen gas in the presence of a catalyst like platinum, palladium, or nickel. And what happens is that the double bond breaks, giving you two hydrogens, right? And if you remember back from previous slide, this was the unsaturated version of the hydrocarbon, right? Because it's missing, since it has a double bond, it's missing hydrogens on both carbons. And this is the saturated version of the hydrocarbon, because now all the carbons are saturated with hydrogens where they can be, right? Assuming that the rest of these are H's as well. The alkene can also react with water, with some acid. That H plus there means acid, right? And then it gets hydrated. And so in a hydration reaction, it becomes an alcohol where part of the water leaves as an OH to attach to one carbon, and the other one, the other hydrogen on the water goes and attaches to the other carbon, breaking the double bond that used to be there. So here's a quick little review or summary. In a hydrogenation reaction, an alkene plus plus hydrogen gas with a catalyst, platinum, nickel, or palladium, will give you an alkane. In a hydration reaction, an alkene plus water and some strong acid will give you an alcohol. Make sure you know that. And so this little example I have up here that just popped up is my example of saturated versus unsaturated, right? Here we have oleic acid, well that's tough, which is a fatty acid. It's a fatty acid found in olive oil, and it's unsaturated, right? Why is it unsaturated? Because we have a cis double bond right here, right? But if you treat that guy with some hydrogen gas in the presence of platinum, for example, or nickel, or palladium as a catalyst, right? You can hydrogenate it, and now the double bond is gone. You have two hydrogens in its place, and now you have stearic acid, which is a saturated fat. So when we're talking about saturated hydrocarbons and unsaturated hydrocarbons, we're basically talking about saturated fats and unsaturated fats. And that is butter, which is, by the way, a saturated fat and is solid at room temperature, right? Guess what? Unsaturated fats are liquid at room temperature, like olive oil. So let's do some practice reactions here. I have CH3, CH, 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 which is just CH3, sorry, which is just butene, right? And I am treating it with hydrogen gas in the presence of the catalyst platinum. What's going to be the product of this reaction? Well, we just saw in the previous slide, right? CH3, CH, 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 CH3. Because remember, an alkene plus hydrogen gas with some kind of catalyst like platinum, palladium, or nickel will give you an alkane. Let's try it with this guy now. We have a cyclopentene here. Alright, cyclopentene plus hydrogen gas, again in the presence of a platinum catalyst. What do we get? We get plain old cyclopentene. Cyclopentane, sorry. Cyclopentane. Right? Because the double bond that was here got hydrogenated. So it's gone now, and now we have two extra H's there. And then, here we have another butene, an isomer of butene, right? This isomer of butene had the double bond in the middle. This butene has the double bond at the end. But as far as this reaction goes, it doesn't matter because it's plus water in the presence of very strong acid. What do we get? We'll get CH3, CH2, CH2 again. I drew it out that way so you see that it's different now, right? And then I'm going to actually remove my head so you can see the rest of this. CH, 2, OH, right? Because remember, when you have an alkene plus a water in the presence of a strong acid, you'll always get an alcohol. Right? Remember that. Continuing on, we can talk about some aromatic compounds now. Michael Faraday in 1825 isolated a hydrocarbon called benzene. Right? Benzene special. Because benzene is an aromatic compound. And what does that mean? It means that benzene has, and you can see it better in these drawings down here, double bonds arranged in a circular manner in which these double bonds can move around the circle like so, so that they used to be in one position, but then they're in the next position afterwards, right? You can't even really see that. Let me draw it bigger. Can't tell you how many hexagons I had to draw when I was in organic chemistry class, right? So if this is benzene, the line angle of benzene, right? I have double bonds there. These double bonds can move around in a phenomenon known as resonance, right? Like so. So that now the double bonds are in the next position over. And that's what makes them aromatic. That's what makes them aromatic. These are flat and very stable structures, right? And this is the ball and stick, as you already know. This is the condensed then this is the line angle, right? Actually, I'm not sure what this is because it has hydrogens in it and it has line angle in it with no carbons. But I'm sure the example is just drawn there so that you can actually see that there are hydrogens there, because there are. But if it's a line angle, it doesn't need to have hydrogens there. That's actually the reason why this circle right here is here in this line angle, because that circle means that the bonds, the double bonds there, are constantly moving, right? In the manner and such that I just drew there, where it's going around in a circle, right? And that's what that circle means. So those are double bonds in there, right? Oh, I forgot to bring myself back. There I am. That's why I felt a little off just now. So that's about aromatic compounds. There's more than just benzene as an aromatic compound, but benzene's probably the most famous, most well known. So here's some more aromatic compounds, right? We've got toluene here, right? So again, this is like a combination of line angle and condensed structure or formula. So a real line angle of toluene looks like this, right? Here's aniline. Here's phenol. Phenol is another very common one. We use that a lot in biology, forensic biology to be exact, to do chloroform phenol extractions of DNA. That's good times. And then here's chlorobenzene. Here's 1,2-dichlorobenzene. Notice that the substituents are named first, right? 1 and 2, with the carbons that they're connected to, right? And then 1,3-dichlorobenzene, right? Same thing as 1,2-dichlorobenzene, except now the second chlorine is on the third carbon, right? Then 1,4-dichlorobenzene means that the fourth carbon is the one exactly opposite from the first carbon. Here we have 3-bromoaniline, right? Why is it just called bromoaniline, 3-bromoaniline? Because we already know that this part is called aniline, right? And the substituent for aniline is always labeled, the carbon that's connected to the substituent of aniline is always labeled 1, right? So that means that this then is carbon 2, and then that's carbon 3, and that's why it's 3-bromoaniline, right? Here we have a phenol, right here. This part right here is the phenol, right? Of course, again, the primary substituent being the OH is where the 1 goes for the first carbon. And we go in the direction of the next closest substituent, which is chlorine, at the second carbon right there. We have a third carbon here with nothing on it, and a fourth carbon with a bromine. And that's why we call it 4-bromo, 2-chloro phenol. Right? Again, we have a aromatic known compound right there, well-known compound right there, which is toluene. This one has bromines on both sides, so it doesn't really matter which direction you go. But it's the same on both sides, so it doesn't even matter. That's the reason why it doesn't really matter. So we'll just go 2 there for that first bromine. Nothing on the third carbon. The fourth carbon has a chlorine on it. And then the fifth carbon has nothing, and the bromine is on the sixth. The fifth carbon has nothing, and the bromine, the last one, is on the sixth carbon. So that's 2,6-dibromo chlorotoluene. By the way, the reason why bromo went first here, both times, is because bromo alphabetically is before chloro alphabetically, right? Yeah, you'd think you'd name it with the carbon's number first, but the first carbon first, but nope, it's alphabetical. Oh, here's your favorite of mine, dinitrotoluene, right? Which is dynamite, right? So again, the named compound here with the substituent is toluene, and I think I said dinitro. It's trinitro. Sorry. And they're at the 2, 4, and 6. They're at the 2, 4, and 6 positions on the benzene ring, on the aromatic ring, right? So that's tri for 3 nitros on the toluene. So 2, 4, 6 trinitrotoluene, TNT. Here's acetaminophen, which is Tylenol, right? That's its common name. But again, we have toluene here. And the substituent connected to the toluene is this group right here, which I do not know off the top of my head. And then we have aspirin here. And then we have vanillin here. And all of these are aromatic compounds. All right.